Hello, molecules and swimming pools. My name is Joseph Moore, and as you can tell by the title, I have been celebrating Mole Day today. No, not that kind of mole. No, that's just the naked mole rat right there. No, not that kind of mole either. I'm talking about Avogadro's number, 6.02 times 10 to the 23rd. Get it? October 23rd, 10 to the 23rd, 1023? Never mind, I wouldn't expect you to get it. Cut the intro. For those of you uninitiated in the finer points of chemistry, let me introduce you to the beauty of the mole. No, not that kind of mole. 1 mole, or Avogadro's constant, is 6.02 times 10 to the 23rd. This is just an astronomically large number. You probably can't even comprehend how big a number it is. To help you with it though, I set up a couple examples. Imagine you had a measuring tape that was 1 mole millimeters long. That's 6.02 times 10 to the 23rd millimeters. A measuring of that tape would be able to stretch around the Earth. By the way, the Earth has a circumference of 40,000 kilometers. That measuring tape would be able to stretch around the Earth 15 trillion times. But perhaps you still don't understand the monumentality of the mole. The average life expectancy for a human is 80 years. That means you'll probably be living for 2.5 billion seconds, which is 4.2 times 10 to the negative 15th mole. In comparison though, if you convert that into nanoseconds, that's about 4,000th of a mole of nanoseconds that you will live. Keep in mind that there are a billion nanoseconds in a second, so each time a second passes, imagine subdividing that second into a billion. Then you got a nanosecond. So all the nanoseconds of your life concatenated up still will not equal 1 mole. In fact, they'll only be a very small fraction of it. So now you're probably saying, Joe, this mole is so big, how can it possibly be relevant in anything that we ever do? Well, I'm here to tell you, when you apply the mole to very small things, it makes them very manageable. For example, atomic masses. Avogadro's number is such that if you have 1 mole of a molecule, then you'll have that weight of the molecule in grams. For example, H2 has an atomic mass of 2. If you have 1 mole of hydrogen gas, then you will have 2 grams of hydrogen gas. The concept of the mole is really important in chemistry because the amount of the particles matter more than the grams of it, or the mass of the stuff you have. Because different atoms weigh different amounts. If you have 2 grams of hydrogen and 1 gram of oxygen, they won't all just make water. But if you have 2 moles of hydrogen and 1 mole of oxygen, then they will form 2 moles of water. So in a chemical formula, the numbers in front of them mean the moles that react with each other, not the grams of it per se. Moles, in addition to being able to convert grams of a substance to moles of a substance, can also convert volume. For any gas at standard temperature and pressure, 1 mole of a certain gas will occupy 22.4 liters of space. That is every molecule, from small molecules like helium to large molecules like sulfur hexafluoride. Moles are especially useful in converting when you know the concentration of a substance. One definition of concentration is moles per liter, or molarity. That means you have 1 mole of atoms per liter of solution, or 1 mole of whatever molecule that you're measuring concentration of. So 1 mole of solution of HCl will have 6.02 times 10 to the 23rd molecules in it per liter of that just dissolved in. The mole is the common factor between all of this. And because of that, you can convert something from grams of something to know how many liters it would occupy. Or you can know what the molarity is to find out how many particles of something there is. The entire reason why we can do chemistry with any accuracy is because of the mole. Alright, follow me, we're gonna do some science. Now, I was going to make you 1 mole of brownies today, but I thought that might take a little while, so instead what I'm going to do is I'm going to measure the amount of sugar in moles that I used in those brownies. Alright, so the recipe calls for 2.5 cups of sugar, and in case you didn't read that what I have right here is 487 grams of sugar that I measured 2.5 cups. Assuming that the sugar that I used is pure sucrose, whose molecular mass is 342 grams per mole, there is actually 1.42 moles of substance in this thing. So, and assuming that this is going to make 15 brownies, that's going to be about 0.92 moles of sugar per brownie. AP Chemistry Set 7, you guys are in for a treat. Bye.